intercept. And we need to talk a little bit more about how do you go about solving some of these equations. One of the things I'm going to do, I think, today is to show you on a TI-84 how it works. I've got one of the little emulators here so you can see it up on the screen. If you're going further calculus or anything like that, you really need one of the graphing calculators. Okay, depending on the direction you're going, it may or may not be a meaningful thing, but just in case you're headed that way, that's something you're going to need. Okay, so let's take a look at what's going on here. We're in section 2.2. And in 2.2, last time we had talked about the idea that if you have some kind of a function, that function can have multiple roots. Roots are values where the function intersects the x-axis. Very important to keep in mind, if it's intersecting the x-axis, the value on y is 0. Okay? So, we want to keep in mind that solutions, roots, whatever you want to call it, are locations where the function touches the x-axis. It's where the y value is 0. Now, there are all kinds of ways to go about solving to find where an equation equals 0. Or, for that matter, finding where, if you have something like this, let's say we have the square root of 3 times 2x minus pi equals a negative 1/3 x. In this case, we have two equations, two functions, one equal to the other. And you want to figure out where these two things equal. Well, this can be rewritten as a single function, square root of 3 times 2x minus pi plus 1/3 x equals 0. There's our beloved equals 0 again, which would mean that if you could graph this thing and find where it intersects the x-axis, you'd be in good shape. Because where it intersects the x-axis, those x values are the values that will work in that particular function. In this function, any idea how many values of x we're going to look for? Does this have 1, 2, 3, 10 different roots? Any idea? Okay, and you know, there's really no good reason why you should know. Maybe you ran into it somewhere, or just taking a crack at it. If you're just taking a crack at it, wonderful. You know, if you don't try anything in life, it's going to be a mighty boring life. Just use wisdom on what you try. Okay? The highest degree of x here. What's the highest degree mean? Well, that means the highest exponent on it. Well, to the left we have a 2x, and then to the right of that we have a 1/3 x. Both of them have an exponent of 1. The highest degree tells you how many solutions you can have. So this particular equation has how many values of x that'll work? 1. Okay, does that make sense to everybody? One way to do this is to solve it symbolically. That means crunch it out with the math. Let's go ahead and do it that way. What's the first step? Distribute that square root of 3, isn't it? So what we're going to get is 2 square root of 3 times x minus pi square root of 3 plus 1/3 x equals 0. Everybody okay? Now I'm going to combine the x terms. Normally it would be things like 2x plus 3x, which would just be 5x. However, what we're going to have here is this 2 square root of 3x plus 1/3 x minus pi square root of 3 equals 0. Everybody okay so far? And these two terms here each have an x variable. What that's really going to give us, hey look, this is over 1, isn't it? Do you buy that that first value is over 1? We could get a common denominator and add those two things together. Well, the common denominator would be what? 3. So the first part there, we're going to multiply that by 3 over 3. So we're going to have 3 over 3 times this 2 square root of 3 over 1 x plus 1/3 x minus pi square root of 3 equals 0. Does that make sense, what I did on that first term? I'm working toward getting a common denominator of 3. Well, this first one is going to be 6 square root of 3 over 3 x plus 1/3 of x. And I'm going to move this pi square root of 3 to the other side because that's just a number, isn't it? It's just a number. Now, back in the good old days, if you had things like 2x plus 3x, you would take the coefficients, add them together, and then just write the x next to it, wouldn't you? Which would be 5x. Well, we're going to do the same thing here. We're going to put down our x. They both have the same denominator, so the denominator is going to be 3. We're going to get 6 square root of 3 plus 1 times x equals pi square root of 3. You okay so far? A little messier than what you've tangled with in the past, probably. But it gives you good practice on all the algebra skills. Okay? And realistically, in the real world, are you really going to have 2x plus 3x, or is it probably going to be something a lot messier than that? Okay? The real world's a lot messier than that. Okay. Now, back in the good old days, if you had 5x equals something like 20, what would you do to each side? Divide by 5 or multiply by 1/5. And I'm going to go with the 1/5 here because it'll allow us to do a parallel maneuver on the right-hand side of the screen. This is all the coefficient, isn't it? And what I'm going to do is multiply by 3 divided by 6 square root of 3 plus 1. Does that make sense? But if we multiply the left-hand side by that, we also have to multiply the right-hand side by that. So what we're going to do here is we're going to have our 3 over 6 square root of 3 plus 1. Everybody with me? Now the cool thing is, on the left, the 3 in the numerator and the 3 in the denominator cancel. This 6 square root of 3 plus 1, and that 6 square root of 3 plus 1 cancel. And that gives us x equals, well, let's see, we're going to have 3 pi square root 3 divided by 6 square root of 3 plus 1. And here's your answer for x. Yeah, right. So imagine going into Lowe's and saying, I need 3 pi square root of 3 divided by the sum of 6 square root of 3 plus 1. Feet of chain, please. Gallons of paint, please. That's about the time they call security, right? And escort you to the front door and say, we don't use language like that around here. What would you do with that? If you had to buy that much paint or rope or whatever it might be, you'd have to convert it back to a decimal, wouldn't you? Let's see if this will work. I don't know. No guarantees. Okay, so that's good news. That part shrunk down. I want to keep that there. Now, let's see here. I am looking for, I think it says TI-84. Here it is. And, look at this. Okay, so, doesn't get any bigger though, does it? So how on earth do I enter that thing in? I'm going to press clear first. There we go. When I go to enter that in, I'm going to do parentheses, 3 pi, and pi is, there it is, pi. Then I got to do the square root of 3. There's the square root. Of 3. Okay. I'm going to go over parentheses, divided by parentheses, 6 square root of 3 over plus 1 parentheses. There. Is everybody okay? Then what? Press enter and pray. There you go. 1.433. How cool is that? Okay. Kevin down the math lab helped me get hold of that today. So x winds up having a value of 1.433, and that's an approximation. So I'm going to put a tilde, that's that little squirmy line above the equal sign. It's about equal to that. Does that make sense to everybody? Okay. All right. There we go. I'm just going to let the other thing ride in the background. Okay. Let's take a look at a couple of problems. We've got some linear equations. We're learning how to solve them. We just solved what might be the ugliest linear equation you've ever solved in your life. Is that probably close to it? Okay. Let's take a look at a couple of other scenarios. My wife used to race bikes. She was pretty good. Competed on national level. She went to the national finals, bike racing. Okay. It was crazy. To warm up, okay, they would do like a 100-mile race. And to warm up for it, she'd ride 10 or 15 miles on her bike to warm up to race 100. Most people, at the end of the 10 miles, they're sucking air and done. She's warmed up. Okay, but survey, and this is example 11 in section 2.2, finds that 76% of bikers, this is people riding bicycles, don't wear a helmet. Don't do that around Becky. You'll hear it again and again and again. Okay. They found that across the U.S., there are about 38.7 million bikers without helmets. The question is, how many people ride bikes? Aha. Well, the 38.7, is that the total amount or a portion of them? It's a portion, isn't it? That's the folks who don't ride bikes, and then there's some chunk of them who do ride bikes. Okay, if you take a look at the stats, it says 76% don't wear helmets, which means what percent do? 24. So is the number who wear helmets going to be bigger or smaller than 38.7? It's going to be smaller. That's important because sometimes people will come up with some interesting answers and not give any thought to, well, wait a minute, my answer is supposed to be smaller. And just write down the answer and keep going and not even have thought, you know, this isn't right. Okay, so how do you go about doing this? What we want to know is how many people are there total? Well, the total amount is what we don't know. So we will cleverly give it a name like, would be a good name for the total amount that we don't know. T for total. There we go. I was thinking X, but we'll go with total. Either will work just great. Okay? That we don't know. But we do know that if we take 76% of that total bikers, notice on percentage, when you're actually doing some work with it, you don't use 76%, you convert it back to a decimal of 0.76. 76%, what that is, 76% don't wear a helmet. How many people is that total then that don't wear the helmets? Well, that's just 38.7 million. Everybody good? How would you solve for T here? How do you find the value of T?
Divide by 0.76.
Yeah. What we're going to do is we're going to take the 38.7 divided by the 0.76. And remember, this number should be bigger because this is everybody. This is going to wind up giving us T equals 50.9. There. So about 51 people ride bikes? Is that what that means? No, there's a little different unit on that. What unit should there be? Million, right? So that would indicate that about 50 million people ride bikes. It's about 1 out of every 7 in the country, if that's an accurate estimate of the people who go without helmets. All right, so this kind of stuff pretty straightforward for you. Okay, bring those on. Give us lots of those on the quiz. There are quite a few other situations where you'll have various formulas. For example, circumference of a circle is 2 pi r. Okay. What's circumference anyway? Is that the straight across, or is it the around, or is it the tall, or what is circumference? It's around. So that's around the outside of it. Okay. So you've got some lights strung around the edge of the swimming pool. And you know what that distance is because you just bought 3 sets of lights, and each set of lights was 25 feet long. So what is the circumference of the pool? You bought 3 strands. Each of them is 25 feet. The circumference is 75 feet, isn't it? Does that make sense? And somebody says, well, gosh, what's the diameter of the pool? How far across is it? Well, 75 feet accurate? No, because that's how far it is around the edge of it, isn't it? That's not how far it would be to swim across it. How would you get the distance across the pool? Could you from this information? Well, you know the circumference is 75 because it took 3 strands of lights. 2 pi r. What's r mean? Radius. Now is the radius all the way across? No. Thank you. It's only halfway. Okay, but we can work on something from there because we can take this 75, divide it by, now I'm going to do parentheses, 2 times pi parentheses. So what I've put in is 75 divided by parentheses 2 times pi parentheses. Oh man, Chuck, I don't have one of those calculators. Mine does not have pi on it. If it doesn't have a key for pi on it, what number could you put in? 22 over 7. Okay, 22 over 7 or 3.141. Okay, so you could plug in probably 3.141 is pretty decent. Okay, so if you don't have pi as a key on your calculator, just use 3.141, either way. And when you do that, what's the radius? Are you getting 11.9? 11.9 what?
936.
Okay, what units is it going to have on it? Feet. Okay. Is this sounding normal or reasonable for a swimming pool? That's right. This is the radius. This is from the center of the pool to the edge, isn't it? But we wanted to know what? All the way across. This is going to give you a radius of 11.9, which will give you a diameter of about 23.8 feet, which is 24-foot pool. Now, before you go telling everybody, you want to think about for a minute, does this number make sense? Have you ever heard about or seen about a pool that's a 24-foot circular pool? That's kind of standard size, isn't it? Oh, well, that sounds doable. What if you would have come up with the diameter equals 2.4 feet? It's like a kiddie pool. It's like this wide. It's like something you wash your feet in before you get in the pool. Okay? Or if you would have come up with something like this, that's not a kiddie pool anymore, is it? Okay? So be on guard. Think carefully when you get the answer. Does this really make sense? Is this possible? Okay? Because I've seen some amazing answers. I'm trying to think of some of them. When I've asked people various questions, and some of the answers they come up with are entertaining at the least. On one of them, I was asking folks to figure out how much concrete they would need for a driveway. And somebody was going to order up 5,000 truckloads of concrete for their driveway. And they were good with that. I'm thinking you're not so good with that. 5,000 truckloads would cover the entire neighborhood, wouldn't it? It'd all be your driveway. So think about, make sure that things are making sense. All right, let's take a look at another example of a problem that involves linear functions. All right. Out at the farm, we've got tanks like fuel tanks, water tanks, all kinds of tanks that need to be pumped. And obviously with fuel tanks, you're pumping fuel out of them. With water, you're pumping water in them to water livestock and all kinds of entertaining stuff. Got a couple different pumps. Let's say that the large pump can fill a livestock tank in 5 hours. So if we're pumping from the pond, it can pump into this livestock tank in 5 hours. It's a pretty big tank. Okay. Cows drink a lot of water. Okay. A cow will drink 30 or 40 gallons of water a day. Easy. And that's before it's hot. Yeah. You know these 5-gallon gas cans? They'll drink 7 of those every day without blinking an eye. Okay. And there's a small pump that'll fill the same tank. And because it's smaller, it takes longer. It takes 9 hours. Chuck's in a hurry. Chuck's usually in a hurry because Chuck usually well, until just found out today, Chuck's always got to be at a hockey game somewhere. So he throws both pumps into the pond and uses them both to fill the tank. How long is it going to take to fill the tank now? Well, let's see, 5 and a 9. So it should take 14 hours, right, with both of them working?
Well, if you do it at the same time, it might be. You do it at the same time.
Yeah, I'm going to take both pumps, throw them in the pond, turn them both on, and let both of them pump water into the livestock tank. So the one's going to take 5, the other's 9, so it's going to be 14 hours?
Maybe 4 hours.
About 4 hours? So you're saying it should be less than either of them. First off, does it make sense that it would be a smaller number? Yeah, because you got 2 things working, don't you?
Yeah.
Does that make sense? So you got 2 things working now instead of just 1, so it should take less time. Not add the 2 times together, which would be longer than either of them by themselves. Of course, when I have my kids do jobs, sometimes it takes longer than either by themselves because they spend more time fighting. Okay. But we are hoping that the 2 pumps are not going to cause problems. So it should be less than 5 hours. Do we know how many hours it takes total to get the tank done? Well, not really. But what we can do is we can say, you know what, this one will do how much of the tank in 1 hour? Right? And this will do how much? 1/9 of the tank? Does that make sense? Okay. Everybody good so far? So in 1 hour's time, the one can do 1/5 of the tank, and the other one can do 1/9 of the tank, or 1/9 of the total job, 1/5 of the total job. And if this is doing 1/5 of the total job, and this is doing 1/9 of the total job, the total job is going to add up to 1. 1 livestock tank filled. Oh wow, now we have to do solve for t. How would you solve for t here?
Find a common denominator.
That's right, find a common denominator. So that means on this first one, go multiply by 9/9. And on this second one here, multiply by 5/5. So this is going to give us 9t over 45 plus 5t over 45 equals 1. Everybody good? Because they have the same denominator, we can rewrite this as something or other over 45 equals 1 whole tank done. And that's going to be 14t, isn't it? Okay so far? How do you solve for t? Yeah. We can multiply by the 45, and that gives 14t equals 45. Then we divide by the 14, and that'll give us 45 over 14. Now, if we're talking about time and we're talking about hours, would it make sense to convert this back to a decimal or leave it as a fraction? back as a decimal, wouldn't it? What time are you going to be there? Oh, about 16/3 hours. It's kind of an unusual way to measure time. But if we do the 45 divided by the 14, oh no, my calculator just died, apparently. There we go. 45 divided by 14 is going to be 3.2. Okay, here comes the tricky part. It's over 3 hours, isn't it? So the 4-hour estimate was a pretty good one. 3.2 hours. Does that mean 3 hours and 20 minutes? No. How many minutes are there total in an hour? 60. So to get the minutes, we're going to take the 0.2 times 60, which is going to be 12 minutes. This then would mean it's going to take 3 hours and 12 minutes to get the job done. Does that make sense how you convert from a decimal back to hours and minutes? Okay. Be careful because folks are tempted to see that 0.2 and think, oh, that's 20 minutes. It's not. Okay, it's 0.2 of an hour, okay, which is 0.2 times 60 minutes. So, total time, 3 hours, 12 minutes, 4 hours is a good estimate. And the nice thing about saying, it might take about 4 hours is we're going to get done early, aren't we? Better off getting done early than getting done late, but you're better off getting done. So if we're ahead of schedule, that's not a bad thing. Okay. Let's take a look at another example here. Let's say we got a situation where you got a runner, and in 1 hour, this person travels a total of 10.1 miles. Or somebody riding a horse. How's that sound? Okay. 10 miles in an hour on a horse isn't quite so bad. Part of the time, the horse is going about 8 miles an hour. And the rest of the time, it's trotting along a little faster at 11 miles an hour. Those are not tough speeds for a horse to do. Question is, how much time was it going 8 miles an hour and how much time was it going 11 miles an hour? Okay, how much of the time was it going 8 miles an hour? As soon as we know how long it was going 8 miles an hour, will we also know how long it was going 11 miles an hour? Let's say it was going 8 miles an hour for 20 minutes. How long was it going 11 miles an hour? It has to be 40, doesn't it? Because it adds up to an hour. Aha. That gives us a quick way to figure out what this is. It's going to be 1 hour minus however much time it was doing 8 miles an hour, doesn't it? The advantage to writing it like this is we still just have one variable, t. So we're okay. We're still with one variable. Okay. We've got some information about distance. We have some information about time. We have some information about rate. Do you know of an equation that will combine rate, time, and distance together? You may say, no, Chuck, I don't have any idea, but you do. You jump in your car, you drive 50 miles an hour for 3 hours. How far have you gone? $150 miles. You go 3 hours, 50 miles an hour, 150 miles, right? How'd you do that? Well, let's see. The distance that you traveled was equal to, where'd you get the 150?
How did I do?
Yeah. Yeah. You take the rate that you're traveling at times how many hours did you travel at that time? Yeah, I've seen that equation before. Now, this may sound kind of silly. The way I remember it is I think dirt. Distance is rate time, where the equal sign is D-I-R-T, dirt. Dude, you've been in the sun too long this summer. Okay? It may sound kind of strange, but it sticks. Do we know what the total distance is? .1 miles. So I could put 10.1 miles over here. Equals. Now we got to be a little careful here because were we doing the same rate the whole time or did things change up a bit? They changed up a bit, didn't they? Part of the time we were doing 8 miles an hour. Well, that would be the rate, 8 miles an hour, times how much time was spent going 8 miles an hour? Do we know? Could it be longer than an hour? No, because the total time you were riding was 1 hour, wasn't it? So it has to be less than an hour. But remember, we didn't know what it was, so what did we call it? Times t. So there's the distance you traveled at 8 miles an hour. Plus, part of the time was going 11 miles an hour. And how much time were you going 11 miles an hour? It was the 1 minus t, wasn't it? Oh, wow. Is this starting to make some sense? This will give you the 10.1 miles equals 8t plus, hey, on this second part, what should we do with the 11 times 1 minus t? Distribute. So we're going to get 11 minus 11t. We have the 10.1 miles equals, well, let's see, 8 minus 11 is a negative 3t plus 11. Everybody good so far? I'm going to move this minus 3t over here, which will give us a 3t. And then I'm going to subtract the 10.1. When you subtract 10.1, what do you get? Come up with 0.9, which means t equals 0.3. And what's the time being measured in here? Minutes, hours, days, weeks, months, years? It's in hours, isn't it? Once again, we got to be careful. Well, how long till you get there? About 0.3 hours. To convert this to minutes, what would you do? There's 60 minutes in an hour, right? Which will give you 18 minutes. Now you got to be careful here because that 18 minutes, is that the total time you were riding a horse? No, what's the 18 minutes referencing? Well, the 18 minutes makes reference to the part of the time you were riding 8 miles an hour. So you rode 8 miles per hour for 18 minutes. And 11 miles per hour for how many minutes? 42 minutes. Does that make sense? One more and we'll call it quits.
Where did the 1 minus t come from?
Okay, yeah, where'd 1 minus t come from? This value here was how much time you were riding at the faster pace. The total amount of time was 1 hour, and part of the time you were riding at this speed. So if this was 20 minutes, how much of the hour is left for the other speed? 40, you're right. How'd you get that? You subtracted. You took the 1 hour minus whatever that one time was, didn't you? And that's what t means up there, the time from the other one. Okay. Here's one. Came in kind of handy a couple years ago. Up at Houston Woods, there's a sailboat on the trailer. They still had the mast up. They were trying to pull it from the dock area all the way over to where they were going to park it. I don't know why they didn't just drop the mast over in the area where you pull them out. But anyway, they wanted to pull it all the way over before they did anything. And as they got closer and closer, there was this electric line crossing over. And they were trying to figure out, are we going to hit this or not? Now, do you want to smack into an electric line with a big aluminum pole? Do you want to even pull it close to the pole? Not so much. Well, there are ways to get stuff like that done. Okay. In that case, there was the boat. And it had the mast. And they knew the height of the mast. Most sailboat lovers know the height of their mast and some things like that. Okay. And using the shadow, we were able to figure out what the height of the wire was. And figure out from the height of the wire if this thing would go under. Really? Yeah, you can really do that kind of stuff. Let's do a simpler example. Same basic idea. In this example, though, let's say you got a light pole. Okay, somebody's 6 foot tall. And they cast a shadow. Now, the shadow that they cast is 8 feet long. Okay. And the other thing to notice is from the pole to the person is 17 feet. And notice also this whole distance here is how big of a shadow the pole casts, isn't it? Does that make sense? So the pole casts a shadow. How big of a distance is the pole's shadow? 25 feet. That's something we can measure on the ground from the pole at Houston Woods. And getting these shadow lengths isn't all that horrible. I mean, just measure what's on the ground. Okay. What you really have there are two triangles, don't you? Do you see that you have this big triangle there? And you also have a little triangle here. And if they both have the same angles, aren't they in the same proportions? Ooh, whoa, pulling up all of your geometry and stuff. So what that really means is the length of the pole, and we don't know what that pole length is, over the whole length of its shadow is equal to the length of this pole, or in other words, the height of the person, over the length of their shadow. Hey, wait a minute. Can you solve that? That's pretty easy, isn't it? Ah, man, I've seen stuff like this before. We get 8x equals 150. X is going to be the 150 divided by 8. Which is going to give you 18.75 feet. What's 0.75 feet mean? Well, it's going to be in inches, right? How many inches are there in 1 foot? 12 inches? But we don't have 1 foot, do we? We have 0.75 feet. What's that going to be? Like 9 inches? So in this case, the height is 18 feet, 9 inches. It was a good thing we measured when we did that with the sailboat, because it was about 2 foot too tall. There have been some giant sparks and spectacular stuff perhaps going on. Okay. Hey, the homework should be fixed and up and running. Folks, I hope you have a good afternoon. I look forward to seeing you all on Wednesday.
This